Okay, in this video we're going to look at the standard error and the central limit theorem. We're going to first start out with getting a sample of observations. We're going to do 30,000 observations that range from -3 to +3. And we're going to do a histogram. Here we have our nice flat level uniform distribution. Now we're going to do a little bit different. We're going to dimension these 30,000 variables into 1,000 samples of 30 observations each. So now instead of raw numbers, we're going to have 1,000 samples. And we're going to take the mean of each of these. So we're going to take the mean of each row of this dimension. So that's going to be that. And then we're going to plot the means of this, the 1,000 means. The next thing is going to be 1,000 means. And look at this. Now it is no longer a flat uniform distribution. It has this nice bell-shaped curve to it. This is the central limit theorem. The central limit theorem says that the means of any distribution form a normal distribution, given that the sample size is large enough. In this case, 30 is usually large enough if the distribution is fairly symmetrical. This 30 doesn't have anything to do with sample size estimation. It's just what satisfies the need for the sampling distribution to be normally distributed. This distribution of means is called a sampling distribution. If we take the standard deviation of this, find the standard deviation is 0.32. Notice also that with this sample, instead of from -3 to +3, it goes from, in the neighborhood of minus to +1. So the means are a much smaller, narrower distribution than the original uniform. So things are gathered from the ends and piled up in the middle. Now what we can do is look at, so this standard deviation was the standard deviation of this sampling distribution of means. What if we compute the standard error for each of the samples, the 1,000 samples? If we find their standard deviation, we divide that standard deviation by the square root of n, which is 30, and then we take the mean of all those estimated standard errors. And that mean is 0.31. Notice that 0.31 is very close to the 0.32. In other words, our estimated standard errors, the mean of them, if we would do 1,000, would be very close to the actual mean of the standard deviation of the sampling distribution. So basically that's what the standard error is. The standard error is the standard deviation of this kind of hypothetical distribution. If you're going to run a study, you don't run 1,000 samples, you run one. And from that one sample, you estimate the standard deviation of this sampling distribution. Now, you're not always, we took 1,000 and we got a number pretty close. When you just take a sample, that number is going to bounce around a little bit more than that, and so it's not going to be quite as close for each individual sample. But the idea is that the standard error is this estimate of the standard deviation of the sampling distribution, and it's important because that distribution is normally distributed, which means that from statistical theory information about the frequency distribution of this normal distribution. And so you can figure out what are the tails. And like a 95, we'll be computing a 95% confidence interval from this, where we're trying to overlap the true mean. Well, let's go on. So let's say we take a normal distribution. What does it look like? So we've got 30,000 observations. We break them down into 1,000 samples of 30 each, and then we take the mean of all those samples and then we plot them out. And there again we get the means of a normal distribution are also normal. If we go down and we take the standard deviation of this sample, we find that it's 0.17. And then if we calculate the standard errors from each of the 1,000 samples and we take their mean, it's 0.181. Pretty close. Those numbers are pretty close together. So the estimate for each sample, the average estimate over time, or over a large number of samples, is equal to the standard deviation of the sampling distribution. Okay, let's do another one. Let's try the log normal distribution. Remember, this one was really skewed. Look at that skewed, giant skew there up to its right skewed with this big giant peak at the beginning. So we'll break that down into 1,000 observations. We'll take the mean of each of those 1,030 samples and we'll plot the histogram. Now, it is closer to a nice normal distribution, but it is still a little skewed. It's getting there, but it's not quite there. If we look at the standard deviation of this sample, it's 0.40. If we look at the mean of all the standard errors of the 1,000, it's 35. So that's not as close as it was on the other observations. The actual standard deviation of this sampling distribution is a little bit wider than we would estimate doing it 30 samples at a time. Just to kind of show you what happens, let's increase our sample size. Let's do a sample that has a size of 100 each. Again, we have this really super skewed distribution, but now we're gonna do 100 samples. We're gonna take the mean of each of those, and now notice it's still got a little bit of a skew, but it's much closer to a normal distribution. If we kept increasing the sample size, we'd eventually get to a normal distribution, from that super stark skew to a fairly symmetrical, normally distributed sampling distribution of means. Again, that's the central limit theorem, says that the sampling distribution of means is normally distributed if the sample size is large enough. And when you have a super skewed distribution like the log normal, you need a much larger sample size to meet the assumptions. All right, that's it.